Get started. Going to give you a kind of heads up of what's going to happen today. We're going to finish 8.1. And 8.1 is going to be, as you've probably already figured out from last time, pretty tough. We're going to spend what's the time we have left going over the last 5 questions where we actually get to do the number crunching. And we'll show you how the questions are asked in the homework and how we would settle them down. This one is like a template for question 10, but many of the others, this template works really fine. Then next week, we will be looking at 8.2, and compared to 8.1, 8.2 is going to be twice as easy or half as hard. And the reason for that is that you'll be able to use SALT to do all the number crunching. What makes it a little bit hard is that there's a lot of stuff that you have to set up to make it work. So you probably need to see a couple of examples of how you set it up in SALT so you know what to do and where to find the answers. So that's kind of next week. We'll get that done. And then with a bit of luck, we'll get the last one, 8.3, done next week as well. And that's chapter 8 done. So we only have one more chapter after that and we're finished. So we're getting rapidly, we're getting close to the end. So let's jump over and show you what question 10 looks like. Then I'll return here and we'll see where some of these numbers are coming from. Now, one of the tricks of the trade here is to read a question like this and understand what all the information is. So, Gentle Ben is a horse at a due drudge. Over the past 8 weeks, a vet has taken this horse's glucose level, and they vary quite a bit, as you can see. The mean of this sample is 93.5, so I know I need to use that. The standard deviation sigma is 12.5. I know I'm going to use that. Although they don't say n equals 8, if you count them and you look here, can you see that it's 8 weeks? So all of those things are in the information. And the first question they ask you is the significance level. But let me read on a little bit further before we look at that. The mean glucose level for a horse should be 85. Does this set of data indicate that Gentle Ben has an overall average that's greater or higher than 85 and using an alpha of 0.05? Well, alpha is a significance level, so that answer is just a matter of typing it in. Agreed? Wasn't much to do there. Now, state the null and alternate hypothesis. So if you remember what we did last time, you go to what you're looking for evidence is. And we're looking for evidence, is the glucose level higher than 85? So they call it H1, I prefer HA. And you see the one that has higher than 85 is the 4th dot. Does that make sense? Now, if they were saying, I'm looking for evidence that it's less than 85, wouldn't we use that dot? Less than 85. Suppose we were looking for evidence that it wasn't 85. In other words, it wasn't normal. We'd pick that dot. You would, sorry, that dot. You would never, ever choose any one that gave you this choice. Because isn't H not always going to be equal to whatever this number is? That's a format that you get. So in this case, is it higher than 85? Is that one? Now, what sampling distribution will we use? This is just a theory, so let me tell you what we're looking at. The standard normal distribution is what gets used. And it gets used, this sentence here, with a known sigma. You don't know what these two guys are because that's what 8.2 is about. Oh, here's Chris. And this one doesn't work because it says unknown sigma. But I do know what sigma is. It's around here somewhere. There it is. It is known. So in this one, we pick that. Right. That is the kind of the way that the intro to these questions are, and they're very similar in each case. Now I'm going to show you the working that we would be using to get all the other stuff that's going to come. So this is pretty much the bread and butter of hypothesis test. Right. H naught. The mean is equal to 85. The alternate, is there evidence to prove it's bigger than 85? We already answered that. Now we're going to get a z-score. The mean, right, of the sample, take away mu over standard error. The mean of this sample was 93.5. Take away this 85. To get the standard error, it's the square root of sigma divided by n. So it's going to be 93.5, take away 85, divided by the square root of 12.5 divided by 8. And then, whoops, I'll let the calculator do that part for me. So clear this out. So a bracket round it, 93.5, take away 85, divided by the square root of sigma, which is 12.5 divided by 8 people. And the answer is 6.8. I haven't finished this question yet. What do you think a z-score of 6.8 is going to lead to? Do you think it's going to lead to a very tiny p-value and so significantly, statistically significant? Do you think a z-score of 6.8 is going to be pretty rare? Okay. What is the normal range that z-scores are in? A typical z-score is between what two numbers?
-3 and +3?
Yes. So if you come across a z-score that's bigger than that, you can be pretty sure that you're going to get a conclusion at the end, but we still have to go through it. If you get a z-score in 0.2, you are not going to get significant result at the end, right? So sometimes you can have a pretty good guess at what's going to happen, but you still go through the process. So that is a z-score of 6.8. Although you cannot see me, I am typing in 6.8. Oh, to how many decimal places did they want? To 2 decimal places. Oh, it's still 6.8. Go figure. That was interesting. Now we're going to get a thing called the p-value. The p-value is the probability that you get a z-score of 6.8 or bigger. Right. How likely it is to get that, or even bigger? That's what we're going to calculate. That's called the p-value. You get it by using this thing called the normal CDF, and it has a format. Always finishes with 0 because that's the mean of the z-score, and 1, that's its standard deviation. And then it goes low and high. So in this case, it's going to go 6.8. I pick 9, 0, and 1. So let me show you how we get the p-value from our calculator. Right, so hopefully you're looking at the emulator. You go second variable, choice number 2. You hit enter. And the numbers I had written down were the 6.8 we just found, or bigger. Now, I'm just picking 9, but you know you could pick 999 if you felt like it. It's just some that's bigger than 6.8. So it's 6.8 or bigger. A mean of 0, a standard deviation of 1, and then I close the brackets. Now I'm going to hit enter, and what's going to happen is we are going to get a really weird decimal, but it's going to be written in scientific notation, I suspect. You see it? Now that guy is 5.26 e to the negative 12. So let me return and show you that guy. As a decimal, that is 0.123, a whole load of zeros. In fact, including that one and finishing that one, there's going to be 12 zeros. And then you can have a 526. Now they tell us in this question to round that fella off to 4 decimal places. What would a number like that look like if you rounded it off to just 4 decimal places? Exactly, a big fat 0. So that's 0 to 4 decimal places. Well, you can't get much smaller than 0, right? So what I'm now typing in is 0. You have a little picture you can choose. Now, is it going to be statistically significant? Well, is the p-value less than alpha? Is 0 less than 0.05? And the answer is yes. It's statistically significant. Now, what does that mean? That means that we can prove here that this horse definitely has a glucose level that's higher than 85, which is it's higher than the normal. So the horse has got something wrong with it. So I'm now going to return to the homework and show you what that would look like for filling in. Well, we've already done the early stuff. Based on your answers, will you reject or fail to reject the null hypothesis? Well, it's statistically significant. And when it's statistically significant, you use that sentence there. You reject the null hypothesis. Basically say the mu equals 85 is wrong, the other guy is right. And that means that guy. So our first kind of start to finish today was question 10. Now, since this thing is up and running, this is going to be question 11. And this is about a hummingbird. And in this case, they got 2, 4, 6 hummingbirds. Their mean weight is 3.75. If I read on a little bit further, sigma is 0.88. And if I read on a little bit further, right at the end, the significance level is 0.05. And we're being asked does the data indicate that the mean length, the mean weight of these birds is less than 475? So we want to find out, is there evidence to prove that the mean weight is less than 4.75? Right. Everything I just said has been written down. I'm now going to take you through the process. And I've got this guy on the left here. And this is the new guy. And I hope that when you see them side by side, you'll see how much they share in common. Right. Question A is you have a null and an alternate hypothesis. We're trying to prove, is there enough evidence to prove that the mean weight is less than 4.75? Is the mean weight nu less than 4.75? Okay, what do you fill in for H naught then? Look at what was filled in here. What do you think is going to be filled in there? I'm getting old here. Older. Okay. So let's emphasize that so the next time we ask, we'll be a bit more comfortable about the question. A hypothesis test always has two sets, right? An H naught and an HA. That's called the null hypothesis. It's just a jargon name for it. And this is called the alternate hypothesis. The alternate always comes from this story. You're going to be asked, is there enough evidence to prove this is bigger than that? This is less than that. This is not equal to that. In this case, less than 4.75. So the mean is less than 4.75. That's the alternate, the thing we're trying to prove. So that guy tells us what's going here. The null hypothesis is quite easy to do. It's always equal to the same number. So if this is less than 4.75, mu will be equal to 4.75. If this is greater than 20, mu will equal 20. If this is not equal to 47, this will be equal to 47. Okay, so next stage, we calculate our z-score. So we're going to go z-score, p-value. Is it statistically significant and then a conclusion? So hypothesis test done. Z-score. This is the formula every time. I am getting feedback here, so I'm going to mute you. There we go. And back to our thing. So the mean was 3.75. The mu was 4.75. So we're going to go 3.75, take away 4.75, divided by the standard error, which is sigma over n, which in this case is 0.88 divided by 6. So we're going to get some weird decimal. I'll do a bracket. 3.75, take away 4.75, close the brackets, divided by square root of 0.88 divided by 6. And I am looking at a negative number, which is totally okay, of 2.6. What did they want here? To 4 decimal places. Are we okay with how to calculate the null and alternate and now the z-score based on the information that you're going to get from the question? Are we good with that? Thank you, Valeria. Got a thumbs up. So part C then is we're going to get a p-value. Now the p-value is basically the probability that something like this happened, right? That you got this. Now the p-value has two distinct directions to go. If the p-value is, if the z-score is positive, then the p-value will be the chance that z is that number or bigger. If it's negative, as it is here, then we're looking for what's the chance that you had z-scored less than that number. So if you imagine visually what's going on here, is if you've got a really rare z-score about here, and you're trying to find out that thing there. That's what the p-value looks like. It's that tiny little bit at the end that says, look, could you get this sample by luck, by chance? And the chances of doing it is the p-value. Well, that's going to now be a normal CDF of this number or less. So if you want this number or less, have you noticed now the difference between the order? You still use a 9, but a negative 9. Now I can use a calculator, and I'll go second distribution, choice 2, a negative 9, comma, a negative 2.6111, comma 0, comma 1, and the answer I get is 0.0045. Now let's do D. Is it statistically significant? Is this p-value tiny enough to be important? Well, we just ask ourselves this one question. Is our p-value less than the alpha in the story? And in this story, it's that guy, right? So is 0.0045, is it less than 0.05? Okay, is this decimal less than that decimal? I could ask. Bailey, is this decimal less than the other one? Is 0.0045 less than 0.05?
Yeah, it is smaller.
It is. Yay. That wasn't so hard. Now, when you say a yes to that, do you know you basically have the same answer? Yes, it's statistically significant. So pick the choice that says, yes, it's statistically significant. What does that mean? It means you've proved that the mean weight of these hummingbirds is less than 4.75. If you ever get a situation where the p-value is not less than that, imagine the p-value is 0.2, then you'd say no. And no means not statistically significant. So we can't say that that's true. And that's kind of the difference between how you would say yes or no to the is it statistically significant. You just check the p-value you just found and you compare it against the alpha in the question called the significance level, which is the name that we give to this guy here. It's called the significance level. Now you see two side by side. You see there's a fair amount of overlap, isn't there? There's a lot of similar things happening in 10 that kind of very similar stuff happens over here. I would say that creating the A, the null and alternate, is very similar. I would say it's identical how you calculate the Z-score. The p-value, well, a little bit different. In one case, you're bigger than that, in the other, you're less. But there's an easy way to check which direction you go. Typically, if the Z-score is positive, wouldn't you be looking for that number or bigger? So you'd go greater. And if it's negative, you're looking for less. So if I get a Z-score of -2, I'm going to be looking Z less than -2. If I get a Z-score of 1.5, I'm going to be looking for Z greater than 1.5. Now, when it's greater, you do the number in 9. When it's less, you do -9 the number. And that's the order. They kind of switch places a little bit. And then the last bit is that p-value smaller than alpha? If it's yes, it's statistically significant and you've proved this. If the answer is no, it's not statistically significant and you haven't proved that. That makes sense? Okay, doesn't make sense. What would you like me to do a little bit more on? I need feedback here to figure out what I need to do. Are we good? Okay, I guess we'll take one thumbs up. Well, that was question 11. Next one's going to be 13. Compare it against that one. In question 13, well, let's show you what the question is first, and then we'll do it so you can get a little bit of idea of how we work on these. Oh, this might interest you, Chris. You like stocks. The price to earnings ratio, P/E, is an important tool in financial work when you're buying stocks and shares, especially. The random sample of 14 large US banks, JP Morgan, Bank of America, and others are given in the following, and this is their price to earnings ratio. And if the price to earnings ratio is big, it could mean that that stock is overvalued, because what you could buy the stock for is 24 times what they earn, which isn't very good average, I would say. So here is a whole bunch of guys. I need to know the number. Well, if you read in the question, you can tell that it's 14 because it says it there, but if I didn't know that, I could just count them. So n equals 14. I need to know the mean of these, and that's 17.1, and they tell me that there. I need to know what mu is. It's 18. That comes later. I need to know what sigma is, and sigma is 5.3. And if I read on, the key to figuring out what we're asked to prove is, does this data indicate that the price to equity ratio or earnings ratio of these banks is less than 18? So is the average less than 18? And we're going to do that with the significance level of 10%. Right. So I've went through that question and I've collected all the bits that we need. We're now going to solve it the same way we did all the others. And then you can take whatever numbers you get and they'll fit in somewhere in the whole answer sheet situation. Okay, so we're going to start with the null and alternate. And you're going to make me happy this time by doing part of the answer for me. So I'm being asked, is the average less than 18? Is mu less than 18? What do we write down in the null this time? Maybe we're having technical issues. Okay, forget that question for a second. Will you say hi if you're here? So go into chat and say hi. I can't see. Okay, we got it. So yous are there. Okay. Poor Bailey, her laptop's dying on her. Right? It's not your fault. Technically. Right, so we are here. That's good. So now I'm depressed again because no one's answered my question. What do I write beside H naught? What do I write here?
Wouldn't you write that mu is equal to 18? Isn't that what it is?
Exactly. I wasn't trying to catch you. It's exactly that. Yes. Cool. We got it. You comfortable with that now? If it's going to be a trick question, I promise you I will say this is a trick question before I ask it, right? I promise I'll do that. Now, the next bit is going to be calculate what's called the z-score, which is this formula here, right? So it's the mean take away mu over the standard error. This is just a formula. The x bar is 17.1. The mu is 18. And the standard error is this ugly looking guy. It's the square root of sigma, which is 5.3 divided by 14. So we're going to get a guy called a z-score. It's a number that kind of tells you how likely it would be to get this sample if that wasn't true, if that was just normal data. So I'll do a bracket around it. I'm going to go 17.1. I'm going to subtract 18. And then I'm going to do the square root of 5.3 divided by 14. And, oops. I did one bracket too many. There we go. And we get a z-score of negative 1.462, well, 463 if I round it off to 3 places because I don't have a lot of room. So in this story, are we a little bit more comfortable about how we generate part A, these two, how we calculate the z-score, which is this. Now the third piece, we're going to get the p-value, which is the probability that you get a z-score is it going to be a z-score bigger than this or a z-score less than this? What are we going to be looking for? Greater than or less? You can look at this one as an idea. So I've been pointing at things to give you a clue. Is it going to be z greater than this negative number or z less than this negative? Which one are we going to find? And it's not a trick question.
Less than.
Yay. Listen. So moving on. Time for the calculator. Second distribution, choice number 2. On our calculator, the normal CDF then, if you want less than this, it's -9, that guy, 0 and 1. It's always 0 and 1. So -9, comma, -1.463, comma, 0, comma, 1. And we are looking at 0.072 to 3 decimal places. So there'll be a place in the homework where you write down the decimal for p-value. Now it might be 3 or 2 or 4 decimal places. You just make sure you work to the accuracy they ask. And now we're on to, is it statistically significant? And it doesn't matter whether it's a bigger than or a less than story, it's always the same thing that you check. Is this p-value small enough to be significant? So is this p-value 0.072 less than whatever this number happens to be? This changes. In this question, it's 0.1. In the previous one, it was 0.5. So we are now doing that guy. Would you agree that this is less than that? 0.07 is less than 0.10, right? So we would be able to say, yes, it is statistically significant. So in the jargon, you would reject H naught. And what would that mean in real life? It would mean we have proved that the average is indeed less than 18. And we've done it in a statistical way that everyone can verify and check. Are we good? We only have one more. Thank you. Chris, oh, I get 2 thumbs up. We're doing better. Cool. So we only got one last one to do. Is it one last one? Maybe it's 2. I apologize, it is 2. So 13, and that isn't 13, I just did that. That's question 12. Okay. Question 13 coming up in a moment. Let's show you what it looks like. Second last question. Right. Nationally, about 11% of the total US wheat crop is destroyed each year by hail. That's unfortunate. An insurance company is studying wheat hail damage claims in a county in Colorado. So a random sample of 16 claims in the county reported the percentage of their wheat lost to hail. And so you can see that one farm lost 17% and another farm lost 3%. Now, since this is in the same county, I would be a little bit worried about just the sheer variation in that. You would, I don't know if hail hits one place more than another, but if it was in a county, I would have expected these numbers to be much closer. But that's not their question, so that's my question. So let's see what we need to know here. In this story, I need to know how many were in my sample, right? So you can read this as, hopefully you can read this on the screen. I'll make it a little bit bigger if that helps. Okay. How many numbers are in that sample? Yeah. Remember, I'm not, if it's a trick question, I'll tell you. The mean X bar is 12.4. The sigma is in here somewhere. If I go hunting for it, I'll find it. Can someone tell me where I see it. Sigma is 5. And alpha, the significance level, is 0.01. Now, this one is the first time we've seen this particular hypothesis. Does this data show that the percentage is different from the national average of 11%? So it's different. So is the mean different from the national average of 11? So I'm going to put all this together. And we'll see what we get this time. Right, this is the first time we've ever had is different from. So let's show you what that looks like. We'll set up the null hypothesis and what's called the alternate. Different from or not the same as. You use that guy. It looks like an equal sign, but it's really a not equal sign with a stroke through it. What that symbol means is not equal to 11, so it's different from 11. And this guy, as always, is equal. So that's how we cope with a situation where it doesn't say, prove to me it's less than the number or bigger than the number. This is what it looks like when you're being asked to prove that it's not equal to, right? It's just different. Part B should be getting pretty comfortable with this piece, the z-score bit. It's this calculation here. 12.4. Take away 11 divided by the square root of 5 divided by 16. So a bracket, 12.4, take away 11, close the brackets, divided by the square root of 5 divided by 16. And that's about 2.504. Well, that's not a great z-score. You know, anything bigger than 3 or less than -3 is going to be a good candidate. That one's kind of borderline. It might make it, it might not. And now we have to get the p-value, which is now going to be the probability that you get a z-score and this guy. Now, there are only two directions you can have here. It's either a z-score bigger than this number or a z-score less than this number. And there is a pretty easy way to tell. I mentioned it earlier on today. If this is positive, you're looking for a z-score bigger than a positive number. If this was a negative z-score, you'd look for z less than a negative. Now, to calculate that, you go to this fella called the normal CDF. He's basically going to tell you what's the chances of that happening. And it's going to be 2.504 or bigger, 0.1. So whenever it is a greater than, the number goes first, then it's a 9. Whenever it's a less than, -9 goes first, then the number. So that's the two different situations altogether. So, second distribution choice number 2, 2.504 comma 9, comma 0, comma 1. And we are looking at 0.006. Now, this is a trick question. I warned you, this is a trick question. We would now go, is the p-value greater than alpha? And you would typically say yes. So is the p-value 0.006, is that less than 0.01? But it's not. When you have a not equal to story, right? Different from 11, a not equal to story, this test changes. You don't check, is the p-value less than alpha? You check, is the p-value less than a multiple of alpha? Does anybody remember it? I think I only mentioned it once. Is the p-value less than how many alphas? What multiple? Going to move this one. Last chance. Okay, you just have to remember the special case. So, is it that fella? And the answer is yes, so it's statistically significant. Okay, we're on to our last guy. Definitely this time. And I'm going to put it on the screen for us. So in question 14, we're doing a hypothesis test on something to do with blood. Total blood volume per body weight in kilograms is important in medical research. For healthy adults, the red blood cell volume mean is about 28. Red blood cell volume that is too low or too high can indicate a medical problem. Suppose this guy Roger has had 7 blood tests, poor soul, and the red blood cell volumes were as follows, and they give you all the numbers. So I know what I need. I need to know N, I need to know the mean X bar, I need to know sigma, and I need to know alpha, and lastly, I need to know what I'm trying to prove. So as I scan through all this stuff, I need to find sigma, so it's 4.75. I need to find alpha, which is the significance level, 0.01. I need to know what the number in the sample is, and I believe there's 7. And just to be awkward, unless I've missed it, they haven't told us the mean, which is the only question they didn't tell us. So what do I need to do then? How am I going to get the mean, since they haven't bothered to tell me it? Last chance. How would I find the mean when all I know is the 7 numbers?
You add all the numbers together and then you would divide by 7.
You nailed it, yeah. I'm now going to probably screw up here, but I'm going to try. So if you can be patient, 34, add 26, add 42, add 33, add a 32, add a 35, add a 30, and then I'll divide it by 7, and I get 33.14 roughly. So for the last one, we had a little bit of work that we didn't need to do in any of the others. But here is everything that we need to know. 7 sets of data. The average is, the sample is 33 and a bit. Sigma is 4.75. The significance level is this. And the question went and said, is there evidence to show that the blood level is not 28? So if you're not 28, you're actually very like that one I did a few minutes ago. So let's see what we get here. Oh, let's not. Yeah. I'm going to give you a few minutes to do this one yourself. And that will convince me, and hopefully you, that you know how to do these questions. So all I'm doing right now is kind of setting up the template. Oops, this one's and oops, I put the 2 in the wrong place, but there we go. And where is that not equals 1? So we can put it there. Here we go. Right, you got 4 minutes. Have a shot at doing this question. It's very similar to 13. Once you've had the chance to do it, I will then do it, and you can check your answer with me. So no pressure. You got 4 minutes from there. Which reminds me, put the 2 in the wrong place. P-value is based on what's the chance that you get a z-score greater than 6.2397. So as not to use up too much of your time, normal distribution, normal CDF, number 2. If you want bigger than this number, it's 6.2397, comma 9. If you look back at the other questions, you'll find I put a 9 in either that position or -9 in this position. So 6.2397, comma 9, comma 0, comma 1, close brackets. And we get one of those ridiculous e to the -10s, which to 4 decimal places will just be a 0. So it really doesn't matter whether you double this side or that side. Is this less than 0.01? Not a trick question. Is this statistically significant? Yes or no?
It's gonna be yes.
Yay, yes. See, that's called feedback. It means that you know what's going on, and that's good. So yes, it is statistically significant. Okay, so if it is statistically significant, what does that mean? It means that we have proved that there is evidence that the blood level is not 28. So this particular person may have something wrong with them. And hopefully they'll discover what it was and they will do it. I guess my next question is,